Welcome back. We are at Laplace transform slide 4B. We are still continuing with LTI system transfer function. This is slide 4B, section 3. So today we'll study LTI system transfer function and frequency response. We have seen that continuous time LTI system can be described by differential equation. However, there are additional equivalent form to describe this differential equation. One is called transfer function and one is called frequency response. They are not totally equivalent, but they will serve different purposes, and we will see them in this section. What is a transfer function? Well, if we are given a differential equation, a transfer function is the description of the output over the input in the S domain. And we start from a differential equation, and then we will end up with a S domain representation of this differential equation with something very important, with zero initial condition. Okay, so you must remember a transfer function describes a differential equation with zero initial condition over here. Alright, let's start. Let's assume we have an n-order differential equation, the ny dt n plus dn minus 1y dt n minus 1, so on until dy dt is equals to, and on the right hand side the x is the input. We also have it with respect to its derivative up to m order, and in most of our cases m is equal to n or less than n. Alright, x is the input, the typical input, y is the output, and h of t is the impulse response of the system. So we have a differential equation describing this system. So what can we do? Well, let's have a concrete example of a second order. So we have a second order system, and let the coefficient be constant coefficients. So we are only focusing on constant coefficients. So all the a's and all the b's are constant coefficients, real numbers. And we write, let's say, this full differential equation over here. Sometimes we are lazy. We do not want to write dy dx or d2y dt squared. We use the double prime to denote a second derivative and single prime to denote the first derivative. Correspondingly, on the right hand side is the same. So we have a second order differential equation, constant coefficient. Okay, now, so what do we do? Well, we want to convert this differential equation into something called a transfer function. The transfer function is the description of the differential equation in the S domain. So what do? We use the differentiation property, and the most importantly, I reiterate, we have to set the initial conditions of the y side to be 0. Okay, only the y. Anyway, let's try this. So the Laplace transform of, let's say, for example, if we do Laplace transform of d2y dt squared, then this will be s squared ys minus y0 minus sy0 minus y dot 0. Okay, now these two guys, these two are the initial conditions, and we are going to, if we are given this value, we are not even going to use them. We ignore them, we set them to 0 when we are looking for the transfer function. This is important. Okay, but of course, if we are not looking for the differential equation, we are just solving the difference. If we are not looking at the transfer function, we are solving the differential equation, then we must include the initial condition. In solving for the transfer function, we must ignore the initial condition. Okay, so what does it give us? Well, if we ignore all the initial conditions, then what we are left with is something quite simple on the left hand side as well as the right hand side. So it means that actually we are also ignoring the initial conditions of the x as well. Okay. Now, when we get that, what we then do is to arrange the x and the y to be on the left hand side, to be a ratio. And this ratio in the S domain of y over x is called the transfer function, the system transfer function. It shows how the output is related to the input. So basically, y of s is equals to h of s multiplied by x of s. So if we are given h of s and we're given x of s, we can always compute y of s. That's the idea. It will transfer from the input to the output. That's what the transfer function does. Alright, then you'll realize that when we manipulate the equations, we'll get the b's on top and the a's below. Okay, so this is the transfer function. So I remind you, in this slide, we introduced the transfer function from the differential equation, and all we did was two things. One is to use the differentiation property, and two, set the initial conditions to 0, and then manipulate it such that it looks like y of s over x of s. That's it. These are the 3 steps.